Hi, welcome to video 20. Today we're going to talk about the mole. And as we talked in class, we said that the mole is a unit of measurement for how much substance there is uh, in a certain amount of that substance. Alright, so a mole is actually a unit that contains 2.03 times 10 to the 23rd particles of that substance. It's kind of like a very large dozen. A dozen contains 12 of something, a mole contains 6.02 times 10 to the 23rd of that something. Now, why in the world do chemists use this? Well, molecules are tiny and it's very difficult to try to manipulate count. Oh, I have 3 molecules of this or 3 atoms of that and I need 6 atoms of this other. So instead we use the mole that contains many atoms and molecules of that substance, so we can actually react them in amounts that we can use, that can actually produce something that we can measure. And in addition, the mole keeps the relationship of the atoms and molecules that you're going to put in a chemical equation. For example, if you're looking at making water, well, you need 2 molecules of hydrogen to react with 1 molecule of oxygen in order to make 2 molecules of water, as we have in the chemical equation that we have right here. Now, if we mix, if we were doing that with atoms and molecules, it'd be a tiny amount. And can it be done? Yes, it can be done. But it wouldn't really produce any significant amount of water. If we want a little bit more, something that we can measure in the lab, we probably would want to work with 2 moles of hydrogen, all right, reacting with 1 mole of oxygen gas to produce 2 moles of oxygen. Why does this keep the same stoichiometry, the same relationship or ratio that we see in the chemical equation? It's because when we look at a mole of hydrogen gas, well, if you have 2 moles of hydrogen gas, we have 2 times 6.02 times 10 to the 23rd molecules of hydrogen. Similarly, if we have 1 mole of oxygen, we have 1 times 6.02 times 10 to the 23rd molecules of oxygen. So when we combine that, we see that it's still the same ratio. If we were just to cancel out the 6.02 times 10 to the 23rd here and here, that would just be give us 2 to 1, which is exactly what we have in the chemical equation. Because the ratio is maintained, we are going to produce 2 moles, or 2 times 6.02 times 10 to the 23rd molecules of water. And that is actually really why we use the mole. This is all about preserving those ratios and actually being able to keep large amounts of this substance. Now, this special number, 6.02 times 10 to the 23rd, is a number that was discovered much later. It was discovered sometime in the 20th century. But it's given the name Avogadro's number in honor of an Italian chemist known Amedeo Avogadro, who in the 1800s actually proposed the idea that equal amounts of substances of gases would have the same number of particles, and that's the main core or idea of the mole. All right, so the mole is just like a dozen. It's something that allows us to count how many particles we have, and it does it very easily. But the problem is, because the number of particles in a mole is so large, and because molecules are so tiny, well, it would take an infinite amount of time to actually measure out a mole if we were counting them. So instead, what we do is the typical method that we do for when we have many things, if we're counting pennies or something like that. If we weigh and we take the average mass of the molecule that we want to use, and then we have the total mass that we have, when we make that ratio, it gives us the number of particles that we contain. So we are going to be using atomic masses and molecular masses in order to create something that is called the molar mass. All right over here. Sorry, I just moved that. I wanted to highlight it. So it's the molar mass, and so it's very important that we recognize this idea of the molar mass. The molar mass is going to be the sum of all the atomic masses of the components of atoms in a substance. All right, and if we have that amount of mass in grams, we will have 1 mole of that substance. So what does that mean? How does that compare? Well, if we have sodium chloride is NaCl, as you know, and it has a molar mass of 58.44 grams per mole. All right, that's a negative to the negative one, just means per something. So in this particular case, per mole. How do we know that the molar mass of sodium chloride is 58.44? Well, we know that the mass of one atom of sodium is going to be 22.99, and one chlorine atom is going to be 35.45. When we add those two together, we get 58.44. Right? If we have a larger molecule, something that has multiple atoms, something like sulfuric acid, all right? Well, same thing, sulfuric acid is H2SO4. If we have two hydrogens, that is 2 times 1.01. We have one sulfur, that is 1 times 32.03. And we have one oxygen, we have 4 oxygens, so that's 4 times 16. And when we add all of those values, all right, we end up that the total molar mass of sulfuric acid is going to be 98.05 or thereabouts, based on my periodic table here. All right, so if we can find out what the molecular mass and what the molar mass of a substance is, then we have the basis for measuring out how much material we have. All right, knowing how many moles you have in a per amount of substance, and knowing how much you're going to need for a chemical reaction, how much you're going to produce, is very important. There's a whole field of chemistry that is called stoichiometry. Weird word just to say ratios. All right, so keep that in mind as well. Stoichiometry is what we're going to be playing throughout this next week. All right, so if we want to calculate how many molecules of water are present in 100 grams of water, all we need to do is calculate the molar mass of water. Once we know that the molar mass of water is 18.02, we can just set up a ratio. 1 mole of water is contained in 18.02 grams of water. How many moles of water will we have if we have 100 moles of water? 100 grams of water. And so we just solve that by doing a quick cross multiplication. We bring these two together and these two together when you are cross multiplying, and you put the two that are actual numbers against each other on the top, right? And then we divide by the one that is across from the x. And I know that you all know how to do a cross multiplication, and this is what we get. We have this basic idea over here. When we put this in our calculators and we calculate, we get that it's 5.55 moles of water. All right, and I'm keeping it to the right number of significant figures. We have 3 significant figures for the mass of the water. All right. If you don't like doing ratios, if you think, oh my God, I hate ratios, well, not a problem. There's also a nice little formula that you can remember. All right. We have that the number of moles, symbolized by n sub x, is equal to the mass of the sample, m sub x, divided by the molar mass of the substance, symbolized again here by m sub x, mm sub x. So if we want to know how many moles there are indeed in 100 grams of water, all we need to do is put, sample is 100 grams. We have the molar mass of water being 18, and when we divide, we get the number of moles, n, which is 5.55 moles. So it's equally straightforward to use this formula. So the idea of the mole and applying the mole to count the number of moles that we have in a certain mass is very, very straightforward. So for class, I want you to first calculate the molar mass of the following 4 compounds that we have here, okay? And then calculate how many moles you're going to have for each one of these compounds, all right? So how many moles do you have of A, B, C, or D when you have 10 grams of each one of the moles above? In fact, I want you to try something else. For 3, I want you, and this is if you're really feeling strong that you can do this, to calculate the number of moles of each element in those 10 grams of the substance. So how many moles of sodium, how many moles of nitrogen, and how many moles of oxygen are present in the number of moles that you have there. You remember that when we talked in class, we talked about the fact that atoms and molecules keep the same ratios, all right? So remember that that 3 there for the oxygen would just be 3 times the number of moles of the compound that you have, all right? So try 1 and 2, and if you can really do the third question that I've given you orally, try that, and I'll see you guys in class. All right, bye.